Subject of today's tutorial is how to recognize oxidation and reduction reactions. We will have a closer look to this question with this example of two transformations of cyclohexene. But first of all, please keep in mind oxidation and reduction reactions always occur together. Very helpful is determining an oxidation state. For instance, a water molecule consists of three atoms, two hydrogen atoms and one oxygen atom. Atoms always have the oxidation state 0. When the bond is formed, this bond might be polarized. In this case, it is polarized more to the oxygen because the oxygen is by far more electrophilic compared to the hydrogen. So it's polarized, and for determining the oxidation state, we just say, well, okay, the polarized binding electron pair completely belongs to the oxygen. So for each bond, the oxygen becomes one electron more than it has invested into the bond. So the oxidation state is -2. Always use Roman numbers for writing down the oxidation state. On the other hand, the hydrogen has lost one electron, formally lost one electron, so it has the oxidation state +1. In reality, it is polarized. It has a delta plus, a partially positive charge, and the oxygen has a partially negative charge. So let's try that with this reaction. Cyclohexene, two hydrogens are sitting here. Carbon is more electrophilic than hydrogen, so this electron pair then therefore belongs to that carbon, and we have -1 for both carbons, and again, of course, +1 as the oxidation state for that hydrogen, for these hydrogens. Let's have a look at cyclohexanol. This carbon is bound to two carbons. Well, in this time, in these cases, carbon and carbon bond, then one electron for each carbon. The bond of the hydrogen bond completely belongs to the carbon. The carbon-oxygen bond electrons completely belong to the oxygen. Therefore, we have an oxidation state of overall 0 for that carbon. Here, the other carbon, two hydrogens, therefore -2, and that means the oxidation state here has changed from -1 to -2, and therefore this carbon has been reduced. On the other hand, here it changed from -1 to 0. This carbon has been oxidized. Overall, a reduction and an oxidation has taken place. It's some kind of disproportionation, and we don't need, therefore, an oxidizing or reducing agent, just adding water catalyzed by an acid will give us that cyclohexanol. Here, from that olefin to the diol, there is an oxidation, since for both carbons we have a change from -1 to 0. That means both carbons have been oxidized, and therefore we need an oxidizing agent. One oxidizing agent that is appropriate is an peracid. A peracid will deliver one of its oxygens and will be transformed to a carboxylic acid, and as a product we will obtain an epoxide. So also in this epoxide we have oxidation state 0 here and 0 there, -2 at this oxygen. So, and as I said, always when we have an oxidation we should have also a reduction. How about this peracid? Here we have an oxidation state of -1 at this oxygen, -1 at that oxygen. And after transformation to this acid, we have -2 at this oxygen, -2 at the other. So these oxygen atoms have been reduced during this transformation, while the carbon atoms have been oxidized. So now we have the same oxidation state here in the epoxide as in the diol. So we don't need a reducing agent or an oxidizing agent anymore for this final step. It's just the addition of water, maybe acid catalyzed or base catalyzed. We can also transform an epoxide like this to that monoalcohol, but in this case we need a reducing agent for that carbon. Well, a reducing agent is, for instance, sodium borohydride, and this will nicely transform an epoxide to this secondary alcohol. Thanks for listening.